work. It connects here, I plug it into the display and it doesn't show. Nobody has an iPad or all right, we'll figure it out. Maybe it'll work here. It didn't work.
Some students have asked me to extend the submission deadline to the end of the day. And
Sure.
And I think that's also more convenient for all of us. So
Okay.
yeah, so we'll also do that from now on.
Sure. The one concern I have is then at the time we're talking about this new topic, their mind is still on the old one. So why is it more convenient at the end of the day as opposed to 10:30? We can make it the end of the previous day if they want.
Yeah, we can also do that. So let's ask them.
Okay. Yeah. So some people are asking to make assignments due at the end of a day as opposed to by the time of class. To me, it's kind of somewhat important that assignments be due before we discuss the next topic. I mean, we are already discussing the next topic, but before we move too far away. So if the assignments were due today at 10:30 in the morning, we can make them due yesterday midnight, right? Or I'm not talking about any particular assignment. If you need an extension today, tomorrow, that's no problem. I'm just talking in general about when we make assignments due. I'd like to keep them due before class rather than after class. If you disagree and you want to say something either now or privately later or by email, feel free to do that. A word about the due dates and all of that. This is an advanced class. This is PhD level class. We try to be reasonable. We try to treat you like adults. So if you need more time, just ask us. We'll give you more time. If you have a reason. Don't hesitate to ask if you have a reason. If your cat died, if you have a headache, if you just know that the next 4 or 5 days are going to be difficult days for you for whatever reason, you have other, just ask, and it is not going to be held against you. It is not going to be, no points are going to be taken off. Did we go over the class policies, or did we never do that? I think I never did it because I started before they were ready. So let's see if I can get this guy to work. If I can't, I'll just mention the most important things. Laptop. Turn projector on. I want to turn the projector off. No. Screen? No. Screen. So, yep, this is officially not working. Okay.
Have you tried like plugging it in just to the monitor?
No, not yet. Maybe I will. I think maybe it's the wrong iPad type. So let me just tell you what the most important things are. And the most important thing is that you read the policy page and the web page. How many of you have read the policy page? Can I have a show of hands? Not everybody. So make sure you read the policy page because it is binding. You know, it is what we go by. But I'll give you the rough idea of what the policy page says. No, I don't want it here. So basically it says two things. It talks about procedure for extensions and about policy for collaboration and getting help. So if you have an excused extension, namely if you have a real reason that you need an extension, just ask, write to the TA, send a simple email, or you can do it through Piazza. Just write a private note to the TA. There's a way of sending just private note to one person. And say, blah, 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 I need an extension, and say how much you need. It'll save us time going back and forth. Say, I need another day, I need another 6 hours, I need another 3 days, whatever it is that you need. And chances are the TA in charge will write back and say sure, and that's no problem. The other scenario where you might need an extension is when you didn't plan it in advance. The last minute you realize you ran out of time. I try to minimize that, so I'd like you to start working early, but invariably it does happen, some people more than others. And for that we give you a certain number, I think 5 days of last minute extension. So if it's 10:28 a.m. today and you realize you're not done, take one of your 5 days. I'd still like you to send email to the TA in charge, say I'm taking one of the days, so the TA in charge knows not to post solutions or not to discuss it with or whatever. But you can take it the last minute, no problem, but you have a bank of only 5 such days. So after that we'll start taking off points if you do it more often than that. Okay? But the most important one is the one that you can anticipate in advance. Advance could be a day in advance. If your cat died that morning, that's in advance. The point is, sorry, I keep killing the cat. It's just my, sorry, I'll switch to guinea pigs. The point is, be responsible. Let us know as soon as you know that you have an issue. Don't wait until much later. As long as you let us know as soon as you are aware of the problem, we will be very accommodating. Okay? That part is good. 6, 7, maybe less, maybe 5, 6. Yeah, 8. Sorry. Second thing is, these assignments are for the most part based on assignments that were used in the past, either in this course or in other courses. I don't want to change that much because it is very hard to design good assignments. And assignments that have been perfected over the years are worth their weight in gold. I don't know how much assignments weigh, but anyway. So that means that solutions to them may exist in the environment in various places. In your office mates' old files from last year, in your fraternity, you guys are not fraternity, I don't know, maybe some of you, undergrads. In the ether, in the internet, solutions exist and they're easy to get to. Don't do it, okay? It can be done physically. It is not allowed. Do not use existing solutions. Do not consult other people who took the class before, okay? I'm going to rely on your honor and on your common sense. I mean, what you're trying to get out of this is knowledge, not a grade, I hope. I mean, the grade would be easy, relatively. So don't consult other people. Now, you can work. You can consult each other to some extent. You can collaborate with people who are taking the course now. If you do that, disclose that at the top of your assignment. Whether you gave the help or got the help, disclose that you got or gave the help and disclose who it was with and what was the nature of the help. If you solved it together, disclose that as well. There are a few other conditions. If you help each other or if you give each other tips or advice or whatever, whatever you do, you don't take notes at the time. And so no notes are taken. You just look at them and talk to them. Okay? Because that sort of helps ensure that you're actually learning rather than copying something over. So no copying. You have to do it yourself. You have to write your own code. You have to write your own words. But you can discuss the material. This is not legally instead of the web page. What legally binding is the web page. So look at the wording in the web page. I'm just trying to give you the spirit of it. Any questions about that? After having said all that, I should tell you that the assignments are A, fun, B, I think they're very informative and instructive from feedback I got from previous students. And C, I think I mentioned before, it's not hard to get an A in this course. For example, the assignment that was due today is very open-ended. We're going to grade it very liberally. You know, pretty much any ideas that you had would be great, and we might get excited to give you extra credit. But as long as you didn't say something really wrong, you're going to get your points. So don't worry about it. Okay? Any questions? Okay. I took notes here. But I don't see them here. Maybe I'll see them here. Yeah, here they are. Okay, so we were talking about estimators, and specifically point estimators. And we discussed several properties that are desired for them. One of them is having a low bias. We defined what a bias of an estimator is. So we typically have a parameter theta. In the frequentist view of the world, it's fixed, but possibly unknown. Frequentist view. Fixed. Possibly unknown. Usually unknown. In the Bayesian view, drawn a random variable drawn from a distribution called prior. We have data, or we have first of all a likelihood function, which both the Bayesian frequencies approach posit or assume that you know, or that you're going to assume what it is, and it ties the probability of any possible data to the value of this parameter. And then we have data. And then we have an estimator, which is a function of the data. Since the data is random variable, the estimator is also a random variable. And the properties that we said were the bias of the estimator, bias of theta hat, is the expected value of theta hat minus the true value of theta. And we want that to be as low as possible. It's a property of the estimator, of the function with the hat. And there could be multiple estimators that would have different biases. And another property is variance of the estimator. The variance is the second moment around the mean. So that's defined as the expected value of the square. I should put the square inside, I guess, of the difference between the estimator and the mean of the estimator. The mean of the estimator is fixed, is a fixed number given the estimator. This is red, this is blue. Blue minus red is still blue. Squared is still blue. Take the expectation, makes it red. Remember that game? Okay. And we want this to be low, and we want this to be low. And one other thing we might care about that's related to these two is the mean squared error. The mean squared error of an estimator is defined as the second moment of the estimator, a second moment of something, but that something is the estimator minus not the mean of that estimator, but the truth. So variance is second moment around the mean, and mean squared error is second moment around the truth. Second moment around the mean is the lowest possible second moment. So the variance is the lowest possible second moment. And we showed that this can be written as the bias squared plus the variance. So if we care about minimizing this, we should try to minimize both of these things. And if we have a choice between multiple estimators, some of which have a higher bias, some of which have a higher variance, we can kind of combine them together using this formula and decide which one is better for our purposes, if what we care about is mean squared error. I should tell you that actually in language technologies, we rarely care about mean squared error. We care about a different property that's more related to the log domain. We will talk about it in great detail later. But in many other areas, this might be what you care about. A quick sanity check for this. Bias itself lives in the linear space of the parameter that you're estimating. If the parameter you're estimating, theta, is measured in centimeters, then bias is measured in centimeters. It's a linear operator, right? Because bias, this is centimeters, and this is centimeters. The expectation of centimeters is centimeters. Centimeters minus centimeters is also centimeters. Variance lives in the space of centimeters squared. If theta is a length, variance is an area. Right? Because look here, this is centimeters, this is centimeters. The difference is centimeters squared is centimeters squared. Expectation of centimeters squared is in centimeters squared. So if you do a dimension, what physicists call dimensional analysis, comparing the dimensions of the different sides of the formula, you will find that this is centimeters squared and this is centimeters squared. And therefore MSE is also centimeters squared. So don't try to add bias plus variance. That's, you're adding centimeters and you're adding length and area. And that doesn't work. Of course, it doesn't have to be centimeters. It could be anything else. But you get the idea. Any questions so far? So just review. OK. Next thing we need is other desirable properties. So we talked about consistency, right? Consistency, also called asymptotic consistency of an estimator, is the property that as the estimator as a function of the size of the data. So if you have n data items, you can technically when the estimator, the same formula is applied to more data, you can think about it as a different estimator or a different function. But if there's a family of estimators that depend only on the amount of data, let's say your estimator is the average of the data. So you can take average of 5 points or 6 points or 8 points or any number. As long as this converges in probability to the true value, the estimator is considered consistent. So this captures the intuitive notion that whatever the estimator does for a finite amount of data, as you get more and more data, it should, with certainty, with practical certainty, go to the right answer. Can a biased estimator be asymptotically consistent? How so? If it has a bias,
the mean variance, sometimes when it's written 1 over n, is a biased estimator, but it's still consistent in the sense infinity converges to true value.
which estimator?
The sample variance.
The sample variance. As an estimator of the true variance?
Yes, when you have 1 over.
You're right. That is an example of that case. So, but let me first present the difficulty. We said that what does this convergence mean? It means that, among other things, the mean squared error goes to 0. But the mean squared error consists of square of the bias and a variance. So if the estimator as n grows, if the variance grows to 0, that's good. But if you have a bias, if it's non-zero, it could be positive or negative, but when you square it, it becomes a positive quantity. But it can still happen, as you pointed out, as long as the bias itself goes to 0 as n goes to 0. So the bias could be, say, on the order of 1 over n. So there is a finite bias for any sample amount, any finite sample size. There is actually a bias. But as the sample size grows, that bias shrinks enough so that as n goes to infinity, the bias goes to 0. So yes, a family of estimators can be biased, such that any member of it is biased. And yet it can be consistent, because that bias and the variance both shrink to 0. All right, one other property that we haven't discussed yet is efficiency. What does it mean for an estimator to be efficient? Converge faster, or intuitively, it makes optimal use of the data, or it makes better use of the data, and then a maximally efficient estimator makes optimal use of the data. So we can measure it by how fast the variance of the estimator shrinks as you add more data. It is possible to prove upper bound on efficiency. And in fact, there's a very important class of estimators called maximum likelihood estimates, which we'll talk about in a minute. One of the nice properties that they have is that they're maximally efficient. So maximum likelihood estimators are maximally efficient. And as a result, the efficiency of any other estimator can be measured as how efficient it is relative to the maximal possible efficiency, namely to the efficiency of a maximum likelihood estimator. So usually when you talk about efficiency, you talk about relative efficiency. How efficient is this estimator relative to the maximum allowed, relative to the maximum likelihood estimator? So it could be measured in percentages, 70% efficient, 80% efficient. Why would you ever want a less efficient estimator? Well, because it might not be biased, and the efficient estimate might be biased. Or it might have some other desired properties. Okay, any more questions? All right, so all this deals with point estimation. If you remember, we talked about 3 kinds of estimation. Point estimation, interval estimation, and Bayesian estimation, which is basically coming up with a posterior. Remember that? So let's talk a little bit now about interval estimation. In high school, we almost always learn about confidence intervals in like statistics classes in high school, or maybe even in first years of college. And I always found their explanations very confusing and not satisfying. So what they tell you is that you collect some data. That's the confidence interval estimation. Let's do it in the context of a specific problem of estimating the probability of a head in a coin. Estimate P of head. So this is our theta. It's between 0 and 1. Our data consists of n flips of the coin and we got k heads. And anybody wants to suggest a point estimate? A point estimator? Flip the coin n times, I got k heads. I don't know what maximum likelihood is yet, but maybe you mean the relative frequency of heads in flips. Okay, so example point estimation. P head het equals k over n. Now, when we talk about intervals, we say we know that the answer is probably not exactly k over n. If I have a coin that has a probability of 0.6785 of being head, I flip it 3 times. I can only get 0, 1, 2, or 3. I have no reason to think that I've got it exactly right. I flip it 10 times. I have only 11 possible outcomes, right? 0 over 10, 1 over 10, 2 over 10, all the way to 10 over 10. So it gives me a choice of 11 values all the way from 0 to 1. There's no reason for me to think that I got it exactly right. Do you agree with that? And if I flip it 11 times, I get 11 completely different values except for the 0 and 1. So clearly, I'm not going to take that answer too seriously. But what I might say is that it gives me an idea of a neighborhood where the answer is likely to be. So I might take this k over n and add plus or minus something to it. And then I'm told that if I know the formula for what that something should be, I can say with 95% confidence that I got it right, that the correct value falls in this interval between k over n plus that something and k over n minus that something. Do you remember that? Does that sound familiar? It should be familiar to everybody. So let me draw it. And here's my k over n. And my something is going to be something in this direction and something in this direction. And that's going to be my interval. And then I'm told that as long as I chose my something based on the right formula, and the formula takes into account this k and this n, that the correct answer, now I really want to use a different color, the truth falls within a something distance from here. So if the truth happens to be here, then I'm wrong. And if the truth happens to be here, then I'm right. Then I succeeded. This is success, this is failure. And I'm told that I have a 95% probability of success. What does that exactly mean? It turns out it could mean 2 very different things. And they really are different, depending on whether you think like a frequentist or you think like a Bayesian. And it's not just a philosophical difference, they do result in different intervals. So let's look at the frequentist first, because this is the formula that is used in high schools. The frequentist says P head is fixed. Fixed. It is not unknown. What is the random variable here? The random variable is this k over n. Specifically, it's k that's random, and I determined, let's say, in advance. There could be a slight variation of this when I don't determine n in advance. It's more difficult to calculate, but in the usual case, I say, okay, I'm going to flip it 10 times. Once I decide in advance, the only random variable is k. And of course, if k is a random variable, the number of heads I got, then k over n is a random variable too. It's a function of k. And something is also a function of k and n. And therefore, since k is a random variable, something is also a random variable. And therefore, this entire interval is a random variable. So the story that the frequentist tells is that there is a red line somewhere. It's fixed. I don't know where it is. I don't know what it is, but it's there and it's fixed. And when I embark on this procedure of estimation, of flipping it 10 times and drawing the interval, I have to imagine a distribution of intervals. All the possible intervals and each one with how likely it is, given that the red thing is fixed. And 95% of the time, that interval will capture the red dot. Okay? So the red is fixed. The true probability of head is fixed. It's red, and the interval is a distribution. And I'm just counting what fraction of that distribution happens to be a winning interval, namely one that captures the truth. And I want it to be at least 95%. And I want it to be at least 95% no matter where red happens to be. It should be at least 95% if red is here. It should be at least 95% if red is here. Of course, if red is here, the distribution of the intervals would change. And if red is here. In fact, no matter where red is, for any value of p hat, I want 95% of the time, 95% probability that the interval will capture it. Will capture it. Question?
Oh, I just wanted to make sure I understand. So here, there is a distribution of intervals that are moving around.
Right.
95% of them would overlap.
It's not 95% of them. They are weighted by how likely each one is. So it's not like you can count the intervals one at a time. But 95% of the time, you will end up with an interval that overlaps the point. Or you can think about it this way. Since it's enumerable, the intervals are finite because the number of k values is finite. You can assign a weight to each interval based on how likely it is to come up. And subject to this weighing, 95% of the weighted intervals will capture the red dot. Okay? The important thing is that the intervals are random variables. The probability of head is a fixed unknown. And the second important thing is that the statement for the confidence interval formula to be correct, the statement says that for any value of probability of head, this formula will be correct 95% of the time. That's a pretty strong statement because you're not just saying in the world it'll be, in general, in the world it'll be correct 95% of the time. You're saying no matter what the truth is, I have a 95% chance of capturing it. Now let's look at the Bayesian way of thinking. Put it here. In the Bayesian way of thinking, probability of head is not fixed. Probability of head is itself a random variable. Bayesian. Probability of head is an RV distributed according to the prior over probability of head. So remember that the game that the Bayesians play is that they say before this world, there was a God that created many, many worlds, and this world was one of them, and that God decided on what P of H is going to be, and it was different for different worlds. And it was assigned like this, proportionate to this. So we are in one of these worlds, but we don't know which one. But there's a prior probability that we are in a world that has this value. And then the Bayesian consider the data set that you have as fixed. The data, and the data is basically k, is considered fixed. And if k is fixed, then both the k over n is fixed, And the plus minus something is also fixed. Because the plus minus something, that something, if you remember, is a function of k and n. So the something is also red. So the view of the Bayesian is that there is, here's the line. Let's say it's a priori limited to 0 to 1. The data put k over n somewhere and created an interval, this direction and this direction. And this interval is fixed. And now we wonder where P of h is, the thing we're after. It could be anywhere from here to here. There's a certain prior over where it is. Let's say the prior says something like this. This is the prior, P of h, P head. I hope you realize that P of head is another name for theta. It's what we called theta all along. It's just in our case we're talking about a coin, so I call it P of head. But it's the same thing as theta. And this is a prior, and we're going to use Bayes' formula to calculate the posterior. And the posterior may look something like this. This is the posterior. And if a prior is a random variable, it's blue, it's a distribution. The posterior is also a distribution. It's the probability of P of head given the data, given k and n. So we simply use the data to modify, improve our distribution of the thing we're interested in. And now we want an interval. For us to be correct, the definition is that what's captured here what's captured by our most up-to-date posterior is 95% of the mass. That the mass of this distribution is at least 95%. To see that the two are very, very different, consider a case where you have an extremely sharp prior. The prior looks like this, like very, very concentrated near the 1. Now if you flip the coin 10 times and you just happen to get just 3 heads, even though you should have gotten between 9 and 10 heads, the frequentist, of course, doesn't see the prior. If you got 3 out of 10, it'll give you a confidence interval around 3 plus some, minus something. But the Bayesian will consider the prior and would actually put their confidence interval here. If this was the prior, the posterior might change somewhat, but it would still be concentrated here. So the two definitions of confidence interval are completely different. In the frequentist view, the truth is fixed. The data is a random variable. The intervals are random variables. In the Bayesian view, the interval is fixed. The truth is actually a random variable in a meta world. Question?
If you have a flat prior, do they coincide?
Good question. I don't think so. So a flat prior means that your posterior is proportional to your likelihood. Well, here's one reason why they don't coincide. The Bayesian confidence interval is not uniquely defined. You can take this 95% mass and shift it a little bit to the right, increase it a little bit here and decrease it a little bit here, making sure that you're staying with 95%. And that's also a 95% interval, right? So you can, now you can do something somewhat like that in the frequentist case, right? You can have a one-side distribution, two-side distribution, but I don't see a priori that they would be the same.
I think the frequentist one is supposed to be the shortest interval that captures it 95% of the time. So
Is that right?
in the Bayesian case,
You can definitely define the shortest interval.
that would be to me.
Yes. So maybe they are the same. I don't know. It's a fair question. The most important thing about it is it's a different way of thinking. And one of them incorporates a prior, the other one actually I find, even though you may find the Bayesian view very compelling, and many, many people find the Bayesian way of thinking extremely compelling, there is something something extra about the frequentist view. It does not assume that you know a prior. It does not, it says this procedure will always work regardless of what the truth is. So specifically, it will work under conditions when the prior is this or that. It doesn't matter what the prior is. It doesn't rely on the notion of a prior. There's something very, very strong about this, about saying this procedure works no matter what the truth is. Question, Kenton?
Yeah, I was going to ask, like, what's the kind of benefit then of one way or the other over the other if you have like this frequentist where it's like, okay, we're just going to deal with, we don't care what the truth is or this prior. So why would we ever consider it Bayesian?
Right. It's a very good question, and it's a good time to discuss the philosophical debate between the frequentists and Bayesians. So here's how the debate goes, or rather, this is how it went in the beginning. I'm sure today it's a lot more sophisticated. The first thing that frequentists say is exactly what you said now, is, you know, why do I need to assume anything? You guys, you Bayesians are assuming stuff. What if you're wrong with your prior? To which the Bayesians typically say, yeah, we could be wrong, but you're also assuming stuff. You're just not admitting it. And what you're assuming is similar to what you, Liz? What Liz was just saying is you're usually assuming a uniform prior. And that's actually a very kind of wobbly assumption, because uniform prior can change the answer depending on its uniform over what. Right? If you slightly reparameterize the space, then uniform in the new space might give you a completely different answer than uniform. So making the uniform assumption, even though you might think it's a reasonable assumption, it is still an assumption. And there's something arbitrary even about that assumption. This goes back to debates by Laplace and who else lived around that time? What? Oh, I thought you were going to tell me who else lived around that time. I'll get to you in a minute. I don't know if it's Renaissance 1600. Is that Renaissance? Yeah, kind of. When probability theory was just starting, the first question people were asking was, well, what probabilities do you assume when you don't know anything? And the trivial answer was, assume everything is equally likely. But it's actually tricky, because what is everything? How you structure your space defines how you count things. So the Bayesians come back and say, you're assuming too, and what you're assuming is somewhat arbitrary, and you're not even admitting that you're assuming. So there. To which the frequentist might say, yeah, maybe we're assuming too, but our assumptions are sort of the more general principle, whereas you guys are getting your priors out of thin air. Right? You're completely arbitrary. You can choose any prior you want. And they also say, how do you know that your prior is right? Well, in fact, you cannot know that your prior is right. In fact, theoretically speaking, there is no such thing as a prior being right or wrong. With the exception of if you assign probability of 0 to something that a mass of 0 to something that actually happened. But if you don't assign 0 to anything, you can never be proven wrong. So take the case of the coin. Suppose I assumed the prior that was extremely steep towards 1, but I was wrong, and the actual coin has the probability of close to 0 producing head. I can flip it 1,000,000 times, and I get 999,000 tails, and only 1,000 heads, right? Any normal common sense person would say, your prior was wrong. But no, it wasn't wrong. It assigned a non-zero probability to that possibility, right? So it wasn't wrong. You could say it was surprised. The result that came out was something that I assigned to it a very small prior probability, but it wasn't wrong. I didn't say it was impossible. So in some deep sense, priors cannot be right or wrong. They can be more informative or less informative. A uniform prior is typically non-informative prior. A steep prior is more informative. You can measure the informativeness of a prior by the entropy of the distribution. We'll talk about it when we talk about information theory. So where are we in the debate? Oh, so the Bayesians say we cannot be wrong. And of course, the frequencies say, yeah, but you cannot be proven right either. So what a Bayesian thinking amounts to, it's not a procedure that guarantees anything. It's a procedure, well, the only thing it guarantees really is consistency. What Bayesian thinking tells you is, if you believe this before you saw the data, then you should believe that after you saw the data. It's just one big machine for converting priors into posteriors. Think about it as a sausage machine. In comes priors, and the likelihood function, and data, out comes posteriors. If the prior was correct in some sense of correct, then the posterior is correct. If you believe the prior before, you should believe the posterior after. Or this is how you should update your beliefs in the face of data. It never is able to tell you your beliefs were wrong or to prove to you your beliefs were right, with the exception of the zero that we talked about before. Whereas the frequentist approach can actually do something a little more than that. It does not assume anything about your prior assumptions. It talks about the correctness of your procedures. A procedure can be correct or not correct. If you do your confidence interval estimation correctly according to the frequentist, then you are provably going to catch the answer in your interval 95% of the time. What does that mean? You have 95% chance of capturing it, right? There's no guarantee you'll capture it in the next 100 times you try. But now you have a mathematically guaranteed probability. Now in the real world, I think the Bayesian approach came first. And then Sir Ronald Fisher came around the turn of the 20th century, early 1900s, and pointed out all the problems with it, and advanced a lot of the frequentist view, including the maximum likelihood estimator and the properties of the maximum likelihood estimator. Ronald Fisher is considered one of the fathers of modern probability theory, and I would say would be considered a frequentist. And the frequentist view won in everyday life, in policy making. And the reason is, if you're trying to decide whether to use a certain drug A or drug B, or a certain procedure, to say, yeah, drug A is better than drug B, assuming that my prior is right, doesn't fly in political circle of public opinion. And rightly so, because it's based on certain assumption. And the manufacturer of drug B could say, well, no, my prior is this one. And you cannot decide between two priors, right? So a frequentist approach can say, I don't need a prior. I'm going to make a decision that I know by the methodology of the decision is going to be correct 95% of the time. And that's acceptable.
Is there a way of merging the two viewpoints in the sense that you modify your prior piecemeal based on the data you're seeing?
I wouldn't call it merging the two. It's a Bayesian. Yeah, if we might do that here. I do it in my machine learning class. It's a very classic thing that you can update your prior into posterior in one step or in multiple steps. You'll get to the same answer. So a very typical thing to do is you take your data, you create a posterior, now you get new data. Now your posterior becomes your new prior. And you take the new data and you use that to update it again. Now you have a new posterior and so forth. So today's posterior is tomorrow's prior. That's still Bayesian. That's completely Bayesian. You started with a prior and you keep using it. I'm ready to hear.
Oh, okay. I just wanted to have my opinion. The frequentist approach, you know that it works like a safeguard, right? 95% of the time you're right. But whenever you're right, first you don't know whether you're right or not, and which is more, you kind of don't know how right you are, so how close you are to estimate. And the Bayesian approach, I think, you have to assume something, but then you update the prior and it becomes like people, then you know, okay, I'm closer to
Right. Processing a little bit what you're saying is one advantage of the Bayesian approach is that it gives you at any point a complete picture of the likelihood of every possible outcome, every possible truth. The posterior captures in it everything that there is to say, whereas the frequentist approach typically gives you procedures. Like this procedure will just give you tell it what confidence level you want, and it'll give you an interval, and it's either in or out of that interval. I mean, you can guess that closer to the center is better, is more likely, but it's in and out, whereas the Bayesian approach explicitly gives you a whole distribution. You could get something like that here, because you can say, okay, give me the 95% confidence level, give me the 94% confidence level, the 93% confidence level, give me the 99% confidence level. I'm sorry, it's the other way around. 99 is bigger, 80 is smaller. But so you can kind of build it step by step, but it's not what it usually does for you. I agree with you.
Right, and there is a catch with this, because like people like looking at the confidence interval, okay, like 95% interval is this one, like, oh, in the same experiment, what if we take a 99% confidence interval?
People do
Yeah,
that.
that's not how I'm supposed to do it. You're supposed like to, if you want 99% confidence interval, then essentially you have to do 1,000 experiments on each of the experiments that give this
Right.
confidence interval. Otherwise,
Right. Well, that goes to the correct methodology of hypothesis testing. You cannot delay some of your decisions on how you're going to do it until after you saw some of the results. People do it, but it's completely wrong.
do it all the time.
Right. For example, there's a famous, very famous paper called Sampling to a Foregone Conclusion that shows that if you don't specify in advance the sample size, you can continue to sample until you get above the frequency that you want. And if you stop there, you can show that you have a very good probability of drawing the conclusion at the end that you wanted to draw, regardless of the truth. So you have to be very careful when you choose sample size. You cannot condition it on what you get. It's like, all right, I think this coin is biased towards head. I flip it 10 times. I get 4 heads out of 10. Let's flip it 50 times. Now it's getting 24 heads out of 50. Let's flip it another 100 times. And eventually, it gets over. I knew it. Okay? So that's the thing you have to be careful about. And it goes into the notion of multiple hypothesis testing. When you test multiple hypotheses, you still have the confidence in each one of them based on the original formula, but not in all of them together. So if you're going to test 1,000 hypotheses, if you use a 95% confidence interval, you have to expect that about 50 false hypotheses, or false discoveries will come out on average, right? Because there is a 5% chance for each one of them to just wrongly be outside or wrongly give you the answer that you're looking for. So if you expect that 50 out of the 1,000 things you're testing will wrongly test positive, and it's an expectation, it could be more than 50, it could be less than 50, right? It's probably a binomial distribution if they're independent. Then you need to come up with another test on top of those 1,000 tests that tells you how many positive findings are enough to conclude with confidence that at least some of them are not fake. That's called the false discovery rate. So there's a false discovery rate, and you have to take that into account when you design a test that does multiple testing. Okay? Any other thoughts? Questions? Please.
Yeah, I was just wondering, if it is true that the frequentist approach is one everyday life, why is it the case that the Bayesian thinking is very popular in language technology research?
The answer is that what's popular in language technology research is not truly Bayesian thinking. We use something we call the prior, but we don't often use a posterior. Now is the time to talk about it? Yeah, we should talk about it now. So it's a very good question. Let's go back to our Bayes classifier, or I should say, the so-called Bayes classifier. The winner, be it a parameter value or a category or anything that you're trying to derive with your language technology, I always give the winner a star, and I say that the winner is the one that maximizes over all possible answers. Maybe, I don't know what I want to call it. Let's call it the category. The winning category. The posterior of the category given the data which is the same as argmaxing the product of the prior over the category and the likelihood of the data given the category. Right, this is our classic source channel formula. You should have done it for homework multiple times. You should know it by heart. Now, what is Bayesian here and what is not Bayesian? The move from this to this is definitely Bayesian, because we're using the notion of a prior and we're deriving a posterior. This, you will never catch a true Bayesian holding this in their hand. This is an anathema to a Bayesian. A true Bayesian stops here and says, this is what I know now, or this is what I believe now, rather. I used to believe this. I used to believe the prior and the likelihood function. I got the data. I plugged them in. I believe this now. You want me to give you one choice? I refuse. That's what a true Bayesian says. I will not give you a single choice. If you want me to make a decision, I will make a decision. And the way I will make a decision is I will consider all of these possibilities. I will consider their impact, their cost to me in case I'm wrong. I will average over all of that, and I will give you the decision that will minimize my expected loss. But I will never claim that the answer is to take the maximum value. Taking the maximum posterior is a frequentist cop-out. It's not a cop-out. For the frequentist, it's not a cop-out. The Bayesian thinks it's a cop-out. This method, by the way, is called map estimation. You probably heard that term. Map estimation is maximum a posterior. Maximum posterior or a posterior estimation. So if it's determining the class of something, it's not estimation, it's classification. If this is theta, if this is a parameter of some sort, then we call it estimation. But the idea of maximum a posterior estimation is you choose the value that is the highest value of the posterior function. It's not the only way to choose a single value from the posterior function. You can also choose the median. You can also choose the mode. Also, the mode is the max. So you can also choose the mean. So you can choose the mean of the posterior. You can choose the mean, I mean mean, not min, mean. Mean posterior. Median posterior. And mode posterior. Mode of the posterior. The mode of the posterior is the max. And it turns out you could justify all three. They each optimize a somewhat different measure of loss. I don't remember them all, but I think this maximizes the probability you'll be correct. So it's only meaningful when you have a discrete number of choices, because otherwise you're not going to be correct for sure. This maximizes, minimizes the mean squared error, and this minimizes the absolute square error, I think. Is that right, Yun?
Yeah, kind of agrees with my friend.
Okay. It's, I think that's right. But the idea is that you could come up with different ways of copying out. You have the full posterior, and you can come up with different heuristics for how to choose a single answer. And they would optimize different things. But none of them are Bayesian. The Bayesian keeps the posterior in their hand, doesn't let go of it. That was a great question. Thank you. Okay. So let's talk about maximum likelihood estimation. Until now, we talked about estimators in general. We said they could be anything. What I'd like to tell you now is there's a particular, not a particular estimator, but a particular methodology for deriving estimators that is very good and has good properties. And that methodology is called maximum likelihood estimation. It's a methodology, not an estimator, because it would result in different estimators in different conditions. And sometimes it's just a methodology, it's not an algorithm, because it's not guaranteed that in any particular setup you will be able to apply it successfully and come up with an estimator at the end. Sometimes you can prove that one does not exist. Sometimes you just don't know how to find it. But it's a general recipe. General recipe for coming up with good estimators. So the recipe works as follows. By the way, here we talk about estimators. These are point estimators. So we now live in frequentist land. Okay? Point estimation is definitely frequentist.
Is there any language technology where you would use interval estimation?
Yeah, I don't see why not.
Could you give us examples?
I'm sorry?
Could you give any examples to make clear?
Well, usually confidence intervals are used when the end result is a hypothesis. You want to know if this language is more compact than this language based on finite amount of data, or more whatever than that language.
Those things like annotator agreements, for example.
Okay, let's say this language violates a particular grammatical principle more often than this language. You have a finite sample from both languages. You pose the hypothesis that says this language is at least 10% worse than this one. Or your hypothesis is the difference between the frequency with which this language violates it and the frequency with this language violates it is no more than 0.1. It's easy for me to come up with examples when the end result is a hypothesis to be tested that often leads to intervals. When the end result is a working system, the working systems, well, I think you can come up with things even then. If you have to make decisions on how to translate things, you have multiple choices, and you're trying to balance compactness versus fluency versus accuracy in translation. You have multiple optimization criteria, and I don't know, I'm just thinking.
Wasn't Watson using a lot of interval estimates? If you looked at when I was playing Jeopardy, like I'm 65% confident this like answered 35% of that, and based on like where it was in the game, they used.
But is that a confidence? Is this an confidence interval or just a confidence estimate? Just an estimate, which is a very good thing to have, but it's not necessarily tied to intervals. But I do think it can crop up in many places. It is true that most language technology uses just point estimation and usually a form of smooth maximum likelihood. We will get to that. It's because, you know, here I'm dealing with estimating one parameter and I'm spending hours and hours on estimating it. In language technologies, you have to estimate 2 million parameters and you have to write a paper tomorrow. So you don't have time to do all of that. And you really, what you care about is for it to work rather than anything else. So now is the time to take a segue and to tell you, we had, there's this question of, what is machine learning? Is it really any different than statistics? You know, we at CMU have a big machine learning department and machine learning PhD program, and we're big on machine learning. And if you go back 20, 30 years, machine learning was completely different than statistics. It had a lot of AI kind of ideas in it, heuristics and symbolic representations and all of that. Over the years, this part kind of shriveled because AI, hardcore AI kind of shriveled. But the part that was more statistics-oriented grew, and many machine learner researchers discovered that what they've been doing all their life was really statistics, and that somebody else invented it 150 years before. That happened. So there used to be a period where machine learning researchers were kind of, ooh, I really don't know this stuff, I should. Shit. But these days, machine learning researchers know that they have to know statistics like they have to know math and they have to know everything else. So now the two fields are kind of overlapping, and there are some people who say there's really no difference between them. I wouldn't say all of statistics, because there are parts of statistics that have very little to do with machine learning. But the part of estimating functions and point estimation and classifiers existed in statistics. So why are they two different? Why are they considered two different departments? There are people who say it's the same thing. If you ask Larry Wasserman, he'll tell you it's the same thing. There's no difference. Anyway, we had a retreat of our machine learning department a few years back, and one of the questions we were discussing was exactly that. Is there a difference between them, and what's the difference between them, if there is one? And I gave an answer that won some applause, so I'm proud to share it with you. My answer was, statistics has two properties, and machine learning has two properties. Statistics has on the order of 10 parameters. So their problems typically have 1, 2, 3, 4, 5, up to 10 parameters. And they care about it has to be correct. So you will find a lot of proofs in statistical journals, proving properties of estimators and proving the different methodologies are correct. And machine learning people, they have on the order of 10 to the 6 parameters. And the requirement is it has to work. Right? Traditionally, machine learning systems didn't prove that they are correct. They just showed you some interesting capabilities that they could do. From a statistician's point of view, you didn't prove anything, really. You don't know. Maybe it will not work tomorrow. Well, maybe. Now, of course, these boundaries kind of become more and more diffuse. I mean, statisticians these days work much more with lots of parameters and lots of data, much more than they used to. For one thing, they learned how to use computers. 30 years ago, they barely did that. And machine learning people are more interested in the theory, and they look. So really, the boundaries. But if you look at the cultures and sort of the background from which people come, people in machine learning come from sort of computer science, AI. They want to build a system that does something that nobody else has done before. Whereas people in statistics want to build a solid theoretical foundation. So that's my favorite answer.
Isn't that why the Bayesian statistics is still popular? Because when it comes to applications, you can start up with your personal bias. It may be experience or your prior knowledge, and you can keep on improving it with data later on. And you get faster results.
Yeah. You can also say that the scientific process as a whole, physics, chemistry, biology, whatever, can be thought of as a Bayesian process where we start with some prior notions about the world, goodness knows where they come from, but our intuition or whatever, and then we subject it to certain tests, and we update our beliefs in the face of that. And as you can imagine, there's tremendous amount of philosophical objections that can come up to that. Those of you who know about the philosophy of science know that there's Popper, who proposed that this is how we move around, and then other people came after him and claimed that's not the case, and the philosophy still rages on. But you can kind of think of the scientific process as a process of starting with a prior, updating it, proposing hypotheses, testing them, and so forth. Okay, let's go back to our general recipe for coming up with good point estimators. And it is a frequentist recipe. It's the hallmark of frequentism. And you start with a likelihood function. You write down the likelihood function. I'm back to using theta, because I'm back to thinking about the parameters. But it's kind of interchangeable with, if it's a language technology and you're trying to classify, it could be the classes you're classifying into. And now I want to come up with a formula for a particular estimator that is a property of the data. Here's my formula. This is it. The formula is, write down the likelihood function, which is a function of both the data and the parameter. But now plug in the data. You plug in the data. What remains variable now is the parameter. Now this is philosophically a switch, a flip of thinking. We're used to thinking of the likelihood function as you have a fixed parameter, and the data could be anything. So we're used to thinking about this is fixed, and the data is changing. But the maximum likelihood principle does the opposite. It says, the data is now fixed, plugging it in. Now consider all possible thetas. And settle on the theta that gives you the highest value. Now this is only a recipe, not a full, because it doesn't tell you how to do the maximization. Sometimes doing the maximization is easy. Sometimes it's hard. Sometimes it's so easy that you can write a simple formula that gives it to you right away. And sometimes it's so hard that you don't know how to do it. And sometimes it does not exist. There is no single theta that achieves the maximum. And sometimes there could be multiple maxima. Right? So it's not a full-blown estimator. It's not a fully specified formula, but it's a recipe. This is how you go about getting the estimator. Why? Understanding why this is a good recipe is long and complicated. You can write a whole book about it, and I don't know it very well myself. What I do know is that it has some very good properties, and I'll tell you what these properties are. So whenever you do that, this estimator is called the maximum likelihood estimator. So I'll write it with the ML here. And what we know about maximum likelihood estimators is the following. Well, we know a lot, but here's what I remember. They're usually unbiased. I say usually because there are cases when they are biased, and in fact you're going to run into one of them sooner than you think. But the most common kinds of maximum likelihood estimators are unbiased. Second property is that they are asymptotically consistent. So that means with enough data, they're guaranteed to converge to the right answer. Yes, that's I was just repeating what the consistency means. And they are maximally efficient. This is one of the things that Ronald Fisher proved. Maximally efficiency, to remind you, has to do with the rate at which the variance shrinks as the amount of data grows. Or alternatively, it has to do with how much information you're extracting from your data. And a maximum likelihood estimator, if one exists, is the most efficient estimator among all estimators that have the same MSE. I don't remember what the condition is, some condition. But it's the most.
This property of maximally efficient, is it dependent on whether your objective function has a closed form solution or not?
Your objective function?
Your likelihood thing that you're
Oh,
trying to maximize over?
I don't think so.
If you have a closed form solution, then does it matter really whether at what rate the variance shrinks?
A closed form solution to this?
To the argmax.
Well, suppose I have a closed form solution to the argmax. So I have in my hand a closed form description of this estimator.
Right, then you don't really worry about the rate of converging itself.
Well, I do, because it's a completely different process. This is the process of generating the estimator from the data. But now I'm thinking about, suppose there's another estimator. Let's suppose I have only 1 million data points. And I'm trying to get the best estimator I can, in some sense of best. I can derive a maximum likelihood estimator and use that on this data to derive an estimate. But there may be another estimator that might have other desired properties, and who's to tell me that this estimator is better? I don't know if, I guess I'm not answering your question.
Maybe I'm thinking about it.
All right, think about it, let's talk about it more later. So these are the things that I remember about how good MLEs are. They're usually unbiased, asymptotically consistent, they're maximally efficient. Do you remember the list of desirable properties that we had? It's very similar. What's missing from this list? Low variance. So maximum likelihood estimators don't necessarily have low variance. They have the lowest variance in their class, where I don't remember the definition of class, among all estimators that have, do you remember?
I think it isn't unbiased. I think it would be among all unbiased estimators.
Okay.
But there's some conditions that.
Right. Among all unbiased estimator. So that is definitely true. But I think it's actually stronger than that. Even among estimators that are biased, they could be more efficient under some broader conditions. But at least this condition is true. They're more efficient than any other unbiased estimator. But that leaves the possibility that there is some biased estimator that is more efficient, that has a lower variance. And that's not surprising. We can trade off bias and variance. So if you're willing to have some bias, you could have maybe much lower variance. So that's the good news. The bad news they can have high variance. And they usually do have high variance, especially for small data sets. So just to give you a rough idea, what's a small data set? If you flip a coin 5 times, and you got 1 head, there's a big variance in how many heads you're going to get. So now let's do some examples. Oh my gosh, we're running out of time. We are on a Monday, and your homework requires all of that. Can you stay 5 minutes in class with me? You can also watch the videotape lecture later if you have to leave. So I'll do it kind of fast. I'll leave it like this. Extra marker? No, it's the board. Okay, I'll use this board. All right, you flip a coin, n flips. You got k heads. So your data is n and k. You could even argue that you decided in advance on n, so n is not the data. It's just part of the setup. K is your data. Now you want to write the likelihood of the data as a condition on the parameter. The parameter is probability of head. We want to find what value of theta maximizes this. So this would be theta ml as a function of the data, which is k, is the argmax over all possible thetas. Thetas are in the range 0 to 1 of the likelihood function. Now, what is the likelihood of k heads out of n flips where the true probability of head is theta? It's the binomial expression. It's n choose k, theta to the k, 1 minus theta to the n minus k. Right? So now I need to find out what is the value of theta that maximizes this expression. From here on, it's just calculus and algebra. The first thing to notice is that in the maximization of theta, this does not participate. It's constant. So I cross it out. So I only care about this. That's the first trick we do. The second trick we do is we say whatever maximizes the log of the likelihood is the same thing that maximizes the likelihood itself. And because of this form, it's easier to do the log of the likelihood. So that would be the argmax over theta of k log theta plus n minus k. This is just taking the derivative with regard to theta log 1 minus theta times the internal derivative of 1 minus theta, which makes this a negative. I'm sorry. No. I'm not there yet. Sorry. I'm not there yet. So this is k log theta plus n minus k log 1 minus theta. I'm hurrying. All right. Now, to maximize this expression, I can take the derivative and equate it to 0. So the derivative of this is k. Derivative of log theta is 1 over theta, so it's k over theta, plus n minus k times the derivative of log of 1 minus theta, which is 1 over 1 minus theta, plus the internal derivative, which makes this negative. I took the derivative, I equate it to 0, or alternatively, I can just say that this must equal this. I cross multiply both sides. I get k times 1 minus theta equals n minus k times theta. So that's k minus k theta equals n theta minus k theta. I cross out the minus k theta. I get k equals n times theta. And therefore, theta, my winner, is k over n. Whoa! I just derived the incredibly insightful result that the relative frequency of heads is a good estimator. Of course, high school kids would know that. But what I derived is that it is the maximum likelihood estimator. Until now, I only allowed you to call it the relative frequency estimator. And we argued just intuitively that we think it's a good choice. But now we can say it is the maximum likelihood estimator. It's a good choice. Very often, the maximum likelihood estimator will tend to be the relative frequency estimator. But there are many, many cases where it's not, where things get complicated. The important thing about this example is the process we went through to derive the maximum likelihood estimator. We write down the likelihood function. We plug in the hypothetical values of the data, in this case k, and we treat it as a maximization problem. Typically, that involves trying to simplify it, often take the log of it, because maximizing the log is the same as maximizing the original thing, and then at the right time, take the derivative, equate it to 0, solve it. If you can do that, you end up with a closed form formula for the maximum likelihood. If you can't do that, we'll spend several lectures on what to do when you can't do that. So you do have homework now, and it includes following this process for probably at least 2 more examples. All right? Thank you.